Well, welcome back to this final part of our tutorial on the visceral motor system. And I feel much better now that I've taken care of my full bladder. I hope you don't mind us talking frankly about this rather base physiological system, but it is an important system nevertheless. It's one that has been very important in the evolution of mammals that have used chemical signals in urine as a means for social communication, and it remains an important aspect of human behavior. In fact, so much so that I think there's some really fascinating neuroscience behind the governance of our bladder and social cognition. So I'm going to reflect upon that just a little bit as we go along. But really, my primary goal is to use the governance of the bladder and the control of the motor acts that are necessary to void urine as a way to illustrate the integrated action of the visceral motor system and the somatic motor system. Well, okay, so let's get into this session, and as we do, we will, of course, immediately once again appreciate the complexity of the brain and its extension into the spinal cord as the body's most complex organ system. And we will again be highlighting circuitry that provide for the foundation of human behavior. In this case, a very particular human behavior that I hope you will appreciate in a new way as a result of this segment of our tutorial. So my learning objective for you in this part is that I want you to be able to discuss the interplay among the sympathetic and parasympathetic divisions of the visceral motor system, together with the volitional somatic motor system in the control of micturition. Well, just to be clear, what we're talking about is urination. It's voiding the bladder, expelling urine from our bodies. Well, as I said, this isn't perhaps the most pleasant of topics to spend time together, especially given the diversity of life histories and social values and social norms that I'm sure are represented in our learning community. But again, it provides a wonderful opportunity to illustrate the operations of the central nervous system controlling human behavior. Well, let's identify the key principles that are involved in coordinating the activities of the bladder, and then we'll talk about how they are regulated in order to fill the bladder with urine, and then how to expel that urine from the bladder. So here's an illustration using the male form as our model, illustrating the various neural elements that are conveying sensory signals from the periphery and motor signals out to peripheral structures that govern this process of filling the bladder as well as voiding the bladder. Well, let's begin on the sensory side. So as we can see, there are sensory afferents that grow out from dorsal root ganglion cells that innervate the walls of the bladder. And these sensory signals are mechanosensory receptors that are sensitive to the stretch that is imposed upon the bladder as it fills with urine. There are also chemosensory elements associated with free nerve endings. Our polymodal C afferents, for example, are part of this sensory innervation to the bladder wall. So we're sensitive not just to the distension of the bladder, but also to the chemical environment within the lumen of that bladder. Well, these sensory signals then are conveyed to the appropriate sensory systems. Here illustrated here would be the anterolateral pathway that's conveying this sensory information up to integrative centers in the brainstem. Well, there are important motor elements that I want to identify for you. And let's begin with the sympathetic innervation. That sympathetic innervation is coming down from integrative centers in the brainstem and in the hypothalamus, and it reaches this intermediolateral cell column. And for control of the bladder, we're talking about the lower part of that cell column in the lower thoracic, upper lumbar segments. And the preganglionic neuron grows an axon that reaches one of these prevertebral ganglia associated with the inferior part of the pelvis. And there we find the ganglionic neuron that then supplies innervation to the bladder wall. Not shown in this illustration is additional innervation from the sympathetic ganglia to an internal sphincter muscle that is under the control of the sympathetic system. And this provides for a way to ensure bladder filling rather than bladder voiding by governing the contraction of smooth muscle at the base of the urethra that drains the bladder. Well, finally, the parasympathetic division of the visceral motor system has an important role to play in governing the bladder. The parasympathetic outflow comes from the sacral segments of the spinal cord. It is receiving input from higher brain centers, as we'll talk about in just a moment. And the preganglionic neuron, as you know, will grow a long distance. In this case, it will supply a ganglion that is very close to the bladder itself. And that ganglion will then provide innervation to the detrusor muscle, which is the principal muscle of the bladder wall. Now, let's say just a bit about the functions of these different sources of innervation. So the sympathetic innervation to the bladder is going to promote bladder filling. So it's going to relax the bladder wall. It's going to contract the internal sphincter muscle, and together that will allow the bladder to fill. The parasympathetic system, on the other hand, is going to promote the emptying of the bladder. Activation of parasympathetic inputs to the detrusor muscle will cause that muscle to contract and the bladder to void. Well, in order to actually expel the urine, we have to engage not just the visceral motor system, but the somatic motor system. And the reason is that there is a somatic motor efferent that comes from the sacral segments of the spinal cord and innervates an external sphincter muscle that's in the floor of the pelvis. And that external sphincter muscle helps to ensure the appropriate and timely release of urine from the bladder. So this external sphincter helps to ensure that urine only flows out through the urethra at the appropriate time. So in order to actually void the bladder, one needs to coordinate not just the parasympathetic outflow to the bladder wall, but also the somatic motor outflow to this external sphincter muscle. Okay, so let's see how all of this works. Let's consider first the context of bladder filling. So bladder filling is going to essentially involve an increase in sympathetic activity that will dominate parasympathetic activity. So we're sort of shifting the balance here in favor of sympathetic activity. So in order to fill the bladder, we have to relax the muscle of the bladder wall, that detrusor muscle. And so this is a beta-adrenergic effect, and it allows that muscle to relax when norepinephrine is released via these ganglionic sympathetic neurons. Now, meanwhile, sympathetic activity to the internal sphincter is going to cause that internal sphincter around the base of the urethra to contract. This is an alpha-adrenergic effect. So the detrusor muscle is relaxing, but the internal sphincter is contracting. So by increasing the sympathetic activity, we promote bladder filling. So what that means is that we need to relax this detrusor muscle, and we need to activate this internal sphincter, holding that urine in place within the bladder. Now, during the process of bladder filling, we also want to coordinate the activity of this somatic motor neuron that's supplying input to this external sphincter, exciting that striated muscle, causing it to contract. The more those sensory signals signal the increase in filling of the bladder, the more tone must be generated in that external sphincter in order to remain continent, in order to retain that urine within the bladder. Well, what about bladder voiding? Well, voiding the bladder means that we have to shift this balance. So now there needs to be an increase in parasympathetic activity, where parasympathetic activity now dominates sympathetic activity. So for that to happen, we need to increase the tone of the detrusor muscle. And this is mediated via the muscarinic cholinergic activation of that detrusor muscle. Meanwhile, we want to decrease the tone of that internal sphincter. And this seems to be mediated via a parasympathetic activation of the nitric oxide system. And this causes that internal sphincter muscle now to relax. But what about our somatic motor system? Well, we are not going to void urine successfully unless we have a way of decreasing the output of this somatic motor neuron to that external sphincter muscle. And indeed, this is where descending inputs come into play. There is an inhibitory interneuron that is in a position to be governed by higher brain centers and inhibit the tone of that external sphincter muscle. That muscle needs to relax in order for us to actually void urine from the bladder. Well, how is all this coordinated and governed by higher brain centers? Well, I want to walk you through this. This is an illustration of the neural systems that are engaged when we actually void urine from the bladder. So as I just outlined for you, this involves activation of the parasympathetic system, our preganglionic and then our postganglionic neurons, causing the contraction of the bladder and the relaxation of the internal sphincter muscle. But there's also this inhibition of the somatic motor neurons, which will allow that external sphincter muscle to relax and the bladder to contract and expel urine out through the urethra. Well, this is all coordinated by some really fascinating networks that involve the ventral medial forebrain and key integrative centers in the brainstem. One key center is found in the pons, and it goes by the catchy title, the Pontine Micturition Center. So this center needs to be activated in order to coordinate the lower motor activities that result in successfully voiding urine from the bladder. So stimulation of this structure in experimental animals will produce urination, and it's on that kind of evidence, as well as an understanding of the anatomy, that we recognize this as a key center that must be engaged in order to successfully coordinate this parasympathetic outflow together with the inhibitory signals that relax the external sphincter muscle. Well, the Pontine Micturition Center is under the influence of neurons in the periaqueductal gray matter. This is a fascinating set of cells that surround the cerebral aqueduct in the midbrain. You'll recall that there are networks of cells in this structure that are involved in producing analgesia. That is a top-down means by which we can control the transmission of pain signals in the spinal cord. There's also a center in the periaqueductal gray that can produce locomotion. So different kinds of networks are in this structure, and here's one that seems to be important in integrating inputs from yet higher brain centers and governing the output of this Pontine Micturition Center. Well, the periaqueductal gray receives input from the hypothalamus, hopefully no surprise to you now, as well as the amygdala. And together these structures are governed by parts of the orbital and medial prefrontal cortex. Well, this is where the story of micturition, I think, gets really fascinating, because there remains in human culture still some social dimension to voiding urine. In some parts of the world, it's perfectly fine to void urine in public and to do so without embarrassment, without shame. In other cultures, in other societies, one would not think of voiding urine in public. So one can appreciate, I think, that there is a social dimension to governing the output of this periaqueductal gray in the Pontine Micturition Center. So it's not surprising then that this network in the brainstem should be controlled by parts of the limbic forebrain that are involved in social cognition. Indeed, one of our great neuroanatomists of our time, a Dutch neuroanatomist by the name of Goethe Holstege, was bold enough to publish a paper in the scientific literature that he entitled Micturition and the Soul. And I think what Professor Holstege understands quite well is that there's a certain soulishness about the orbital and medial prefrontal cortex. And this same part of the brain that helps to define who we are as a person, as a human being, within a social context, within a social structure, is also engaged in governing some of our most basal physiological functions, including voiding urine from our bladder. So I, for one, certainly appreciate Professor Holstege's bold proclamation of relating the governance of micturition to the neurobiological basis of the human soul. Well, maybe that's another great topic to kick to the discussion forum if you wish, so I look forward to seeing your thoughts about that. Well, to wrap up our discussion of the visceral motor system, I hope you'll take away from this an appreciation that the visceral motor system operates in coordination with our somatic motor system. It's receiving sensory input, it's receiving top-down signals, even from the highest integrative centers of the forebrain. Well, I think we're ready to bring a conclusion to Unit 4 and our consideration now of our means by which the brain can control movement and mediate various dynamic aspects of human behavior. Where we're going next in the course is to step back, actually quite a bit back, and consider the development of the brain and the important mechanisms that unfold really across the lifespan that account for the changes that our brains undergo from conception all the way through advanced age. Well, finally, we're going to end up medical neuroscience by talking about human cognition. That will be the final unit of the course. Well, the good news is that I think you've had all of the anatomy that you're going to get from me. And now that we've completed our consideration of our sensory and motor systems, what remains in the course is to actually understand that anatomy in a functional context in an even deeper way by considering its embryogenesis, its change across the lifespan, and how these sensory motor systems are integrated at the highest levels of human cognition. Well, we will along the way consider some clinical cases that will help reinforce your understanding of this functional anatomy and how neurological signs and symptoms can help you build a neuroanatomical model of the brain of the patient that might be in front of you, or the spinal cord of that patient, and allow you to localize lesions within the central nervous system based on your holistic appreciation of the function and the behavior and the experiences of that patient. Well, that's a lofty goal. We'll get there by the end of this course, and I just thought I would pause for a moment here and give you a sense of perspective as to where we are in that progression. Well, I do want to leave you in this part of our tutorial with a final study question, and hopefully that will allow you to integrate a little bit of what we've been talking about in this session and maybe prepare you for the unit quiz that hopefully you are about to embark on. And I'll see you on the other side of the quiz when we consider the changing brain in Unit 5.